Good afternoon, class. Welcome to week 10 live problem solving session for electronics course. Today we'll continue with the discussion based on intrinsic capacitance inside a MOSFET. So, a quick recap based on the intrinsic capacitances in the MOSFET. So, this is the MOSFET that we know. Gate, drain, and source, let's say it's an NMOS. So when we say capacitance, what does a capacitance mean? It is basically the change in charge for a small change or small variation in voltage, right? So due to this small change in voltage, there are several types of different capacitances that come into picture, okay? So these capacitances are source like gate to drain capacitance, we call it CGD. Gate to source capacitance, we call it CGS. Source to body capacitance, we call it CSB. And drain to body capacitance, we call it CDB. So we know CSB rarely comes into picture. The reason being source voltage is always equal to body voltage. That is what ideally is considered. So we generally short our source terminal with body. So there won't be any change in charge with change in potential because the potential difference remains zero. So that's why this rarely comes into picture. Otherwise you'll see this is the one which really comes into picture. Otherwise you'll have these three capacitances coming into picture. Okay, with this basic idea, let's move ahead and solve the first question and see if we are able to connect it with previous problem solving session which was held last week. Okay, so in this particular circuit which is shown below, the CS has been given. It is 3.1 picofarads. RS is 43 kilo ohms. GM is 1.47 millisiemens. And RDS is 30 kilo ohms. CGS is 7.4 picofarad. Yeah. So the overall transfer function is to be evaluated for this circuit, and you have to use a Norton's method. What is the pole due to the output impedance? So we have to find out the value of pole. So how do we find out the value of pole? So I'll let you know first of all, see, when there are complex circuits with multiple transistors, so here we have a single transistor, but when there are multiple transistors, and so multiple transistors will give you a number of capacitors, and when you try to solve the transfer function across that whole circuit, it is very tedious, and sometimes it becomes so like it gets so huge that you tend to make mistakes. So the easy way to figure out, what are the things that we get from a transfer function? Let's understand that. So when we are finding a transfer function, what are the things that we have? We have a numerator and a denominator, right? So what are the roots of numerator called? So this, when you turn your numerator to 0, you'll get few roots, and when you turn your denominator to 0, you'll again get few roots. What are these roots called? Numerator, the roots from numerator called?
Zero.
Yes, they are zeros. And the roots from denominators are known as poles, right? So once if we know what are the zeros and poles, we can simply write down the transfer function, right? The moment we know the zeros and poles. So first idea is, rather than go on solving the transfer function and getting your transfer function in this numerator and denominator form, then finding the poles and zeros, what we are gonna do is we are going in opposite direction. So firstly we'll find poles and zeros, and then from there we can build the transfer function. Okay, so it serves the purpose, right? And this, trust me, this method is much easier compared to you solving the transfer function. Okay, so we need to find the poles and zeros. So for this we need to know number of poles or number of zeros, and then value of poles and value of zeros. Okay, to find out poles and zeros we'll need their number and their values, right? So how to find number of poles and zeros? First let's discuss this thing. So let's say with this, okay, so what type of configuration is this? What is the configuration of this particular circuit?
Common source.
Yes, it is a common source configuration, right? So here, now this is your input terminal and this is your output terminal, right? So what are the AC nodes that we have over here? Where will we see the AC signal coming into picture? What all nodes are AC nodes? Will you see any AC signal coming into picture at VA? Yes, correct. Your VDD is DC ground, sorry, AC ground. This is AC ground, that is correct. But what about VA?
DC.
Yeah, this is a DC. So this is not a, what should I say? Uh, this is not a AC node. Okay, so this is also at AC ground, right? So now what are the nodes left where you'll see AC is basically V out and V in, right? Okay. Now number of poles, please keep this in mind. The number of poles is equal to number of AC nodes. Okay, the number of poles is equal to the number of AC nodes. So how many poles do we have in the system? Yes, how many poles do we have in the system?
2.
2, right? Because we have 2 AC nodes. But so ideally there will be 2 nodes. But the thing is, and what is the value of poles? If I talk about the values, it will be 1 upon RC. That is, at that particular node, what is the value of R and what is the value of C. Okay. So when we talk about this input node at Vn, what happens? Your R is infinite, right? At Vn, R is infinite, which makes your pole to infinity, right? So this we generally neglect this pole that is at input, which is or I should say which is at gate terminal. Because of its presence at gate terminal, we generally ignore this pole. Sorry, this will be 0, right? Because 1 by RC, so pole's value will be 0. So at input node, the pole's value will be 0. And because of this, we generally ignore the node which is at gate terminal. Now after that, what is the next node that we have is output node, right? So here what happens, yeah, okay. So here what happens, see, when we talk about a dominant pole, so what is a dominant pole means? What is the sense of a dominant pole? Do you understand when I say a dominant pole? What do you understand from that?
Pole that is closer to origin when we plot.
Yeah.
Yeah,
So the
my
basically it is the pole which will give you the bandwidth.
yes,
Simply speaking.
yeah, or
So
first pole we can say first pole.
yes, yes. So when we plot a frequency response, so what is that first pole which will give you the dip, this particular dip that we get? So this comes into picture when we have the first pole. After this, whatever pole comes, your dip will even get sharper and sharper. But at this particular point onwards, after this particular point, you'll start seeing distortion in your signal. So the basic bandwidth of your circuit will be defined by this initial pole itself, right? So if we get this particular pole, beyond this, whatever the poles are there are of less interest to us. So this is the pole which is we are more interested in. Okay, and if you observe, this is the pole with lowest frequency. So the smallest pole, right? And when I say pole is 1 upon RC and I want smallest pole, that means my RC should be much greater. Is this clear? Because I want my pole's value to be low to find out the dominant pole. That means my value of RC should be much higher, right? It should be towards higher end. So now what we do, so basic idea is when we are asked to find, let's say, the dominant pole or the bandwidth of your circuit, or mm, the point till which your circuit does not show any deterioration or your gain is constant. So when stuffs like when these type of points are asked, so it is basically pointing towards this particular dominant pole that we were discussing right now. So for that, what we do, first things first, we'll go on checking for all the AC nodes that we have in our circuit. Okay, and after that, we'll try to find out like which part, like which of the different. So we have n number of nodes, in which we said like if you see a gate node, the node AC node which is connected to gate, so it is never considered because pole's value becomes 0, so this pole will come at the very beginning, so we generally neglect this. So after that, what is the pole which shows greater like higher values for R and C? We fetch for those. Okay. So since in this particular case we only had one node, so it was not a big issue, right? Now let's say I have another circuit. I'm simply increasing the transistor by one. Okay. Again, let me point out some other nodes as well so it is easy for you to answer. Let's say this node is Vx. Okay, now first things first, what are the AC nodes in this particular circuit that you have in front of you? What are the AC nodes that we have? See, this is the input and this is your output node. Okay, So what are the AC nodes that you'll see in this circuit?
V in, Vx, and V out.
Yes, V in, Vx, and V out, right? And let's say, yes, in this circuit, what are your different AC nodes?
V in, Vx, V out, Vy, ma'am.
Yes, V in, Vx, V out, and V out. V out. So, is this clear? What are the nodes that we are seeing as AC nodes? And why are we avoiding this A, B, C? Is this clear to everyone?
No, ma'am. Can you please repeat, ma'am?
Yeah, so so what didn't you understand? So, is it the question that I asked? Or,
No, no, ma'am. You said no, ma'am. Why we are considering
yeah,
why
yeah.
we are AC
Okay.
node? Why we are not considering A and B and C?
Yeah, yeah. Okay, I'll tell you. So first of all, these A, B, C, the value, these potentials will come from some sort of resistor divider circuit or things like that. And these voltages are basically used to bias your transistor, right? And this will never change because it will come from through a resistor divider circuit which is connected to a VCC. So generally, how you bias your gate? So you'll generally most common method is using a resistor divider bias, right? So here once your R's are fixed, your voltage is fixed, then this voltage will never change. The potential at A will never change, right? So it's more like a DC node. It only has a DC bias. Similarly, B will also have a DC bias and C will also have a DC bias. And we clearly know that while going for AC analysis, when there are nodes which only have DC supply to them, or so those nodes will be AC grounded. That is what we know. Now talking about this point. So what about this particular point? Let's talk about Vy. So what about Vy? Will Vy remain constant throughout?
Yes, ma'am.
No.
Continue.
No.
No, no.
No. Why? Because when you have certain AC signal coming into picture, so this AC, this extra AC will introduce, see, this whole circuit is in series. So it is sure that there is a single current I will be flowing through all the devices. Is this clear to everyone? When
Yes, ma'am.
devices are in series, a single current will flow through the device, right?
Current will not divide, right? Right.
Right. But see, we have introduced, so all other top transistors are fixed biased. So they have a same gate voltage throughout. But what are we doing? At the bottom transistor, we are introducing a little fluctuation at gate terminal. So what this fluctuation will do, it will introduce, so here the VGS now is not fixed. The VGS is changing. So this change in VGS will introduce a delta I amount of current, right?
Okay, okay. Right.
And that current needs to be maintained throughout the circuit, right?
It will get added, right?
Yeah. So what happens now if to maintain this delta I, since this G these potentials at gate terminal are constant for all these top transistors, so what is the uh, condition through which you can adjust the current. So what are the points that you can basically change? What are the points that will change so that your current gets maintained? That is the basic idea, right? So here, since Vg cannot be changed as it is fixed biased, so other points, that is the drain and source potentials, will change. And
VDS.
yes, so if let's say this point, so because of this influence, this point changes, Vx changes. So what will happen? For this C transistor, its VGS is changing as well as its VDS is also changing. So it will
That will
be,
result in V out.
yes, so it will basically adjust that delta I change which we were getting because of this disturbance that we introduced an input, right? So when we talk about AC nodes, we are looking for those nodes which will basically be able to adjust themselves to adjust the change in current that comes into picture because of that input disturbance that we introduce. So that is the basic idea of AC node.
Okay,
Okay?
okay. Means what and all that change in current is happen. It should make you have to make it zero.
Yes.
Like diode operation, ma'am. Switch when
No,
we
no, no.
operation.
That's not what I'm saying. I'm saying, see, when there is a series circuit, the fundamental property of a series circuit is all its components will carry same current,
Mm.
right?
Yes, ma'am. Yes.
So
Voltage will
that
vary.
voltage will vary, but current should
Mm.
remain same.
Yes, ma'am.
Now, because of this small disturbance in input, what happens is we are introducing a delta I amount of change in our circuit. Now, this current change should be uniform throughout all the devices so that my circuit will have, let's say, I plus delta I current, right? Till now, so because of this disturbance, what has happened across this particular transistor, the bottom transistor, here it had the current of I plus delta I, whereas the top transistors were earlier carrying current I. But now, since all these transistors are in series, so all transistors should carry I plus delta I, right? So,
Yes, ma'am.
how is that possible? Because the gate terminal has constant potential in them, but they have to get this extra delta I to maintain that equal current in all the transistors. So how is it possible? So it will try to adjust its other nodes like source and drain nodes. For, let's say, for this bottom transistor, it will affect its this drain node. Now when we talk about the central transistor, that is C, here it has flexibility to adjust its source node, like this one, source node as well as its drain node, because both are floating nodes, none of them are fixed, right?
Yes, ma'am.
Similarly, when we talk about this B transistor, here also it has the capability to adjust either its source node or its drain node, or it can adjust both of them because both are in floating condition. But what about this transistor A?
Okay, okay.
What about
Eight
this
is
transistor A?
okay. We cannot able to adjust, ma'am.
Here we only have one chance, that is we can adjust its drain, but we can never adjust its source because its
Yes.
source is connected to DC. See, DC never changes,
Yes.
DC will remain constant. So what
Yes.
you can change is basically the floating nodes which don't have any fixed values. If I connect, let's say I connect Vy to VDD, no matter what you do, you can never change this VDD. Is this clear?
Yes, ma'am. Yes, ma'am.
So it is, so basically the advantage that we are getting is due to these floating nodes which are present, which don't have any fixed value to them. They change according to the situation. That's why we are able to do this. The moment we connect a DC node to them, or like a DC voltage to them, and they become a DC node, then no matter what you do, you can never change its potential. It will be fixed to pinned to that particular point. That's why we say, no, whenever we are doing AC analysis, we put DCs to AC ground. That means they are not affected by AC signals. That is the basic idea when we say AC ground.
Yes, when we are drawing equivalent circuit, also we will make it
Yes,
DC as ground.
yes, that is the basic idea
Small
because they are
signal.
not
Yes.
influenced by the AC signal coming into picture. Is this clear?
Yeah, yes, ma'am. Yes, ma'am.
Okay. So with this, so hope this is clear. So this was the basic discussion where I wanted to inform like how we figure out what are the AC nodes, because it is the basic thing that we have to find out, like how many AC nodes we have. And with this explanation till now what we discussed, hope it is clear that why that particular node is known as AC node and how to figure out what are the AC nodes. So basically, what are the floating nodes in your circuit? If you can find out those all nodes which are floating in nature, along with your input and output node, will be your AC nodes. Is this clear? Is this clear to everyone?
Yes, ma'am. Yes, ma'am.
Yeah. So once now, so from this, what we are getting is we are finding the number of nodes that we have. So here in this particular circuit, how many AC nodes we had in this bigger one? We had 1, 2, 3, 4. Here we had 4 AC nodes, right? And in this particular circuit, we had 3 AC nodes. Now the next thing is, what will be the value of R and C at that particular node, right? And how to find which how to find which pole is your dominant pole. That is the idea. So oh, I made it all messy. Let me clean it over. Let me clean this a little bit so it's easier. Yeah. Okay, so we'll discuss these two circuits and we'll try to understand how to find the dominant pole. Okay, so in this these are the AC nodes that we have found out. We generally what I said is we'll generally ignore this node, like input node, because the pole's value turns out to be 0 at this particular node, so we generally ignore them. So other than input node, what are the next nodes and what will be the values of them? Depending on that, we'll figure out what is your dominant pole. For dominant pole, what is the condition that I told you? Your RC should be much higher. Okay. So in this particular case, we are left with two nodes, that is Vx and Vout, right? So if you carefully look at Vx, it is connected to drain of one transistor and source of another transistor. So can you quickly let me know, like, what is the resistance value RD is, like RD and RS, that is intrinsic source resistance and intrinsic drain resistance of an MOSFET. Can you quickly let me know? And how they'll come into picture? So they'll come in parallel, right? So you'll see a a drain resistance from here, and you'll see a source resistance from here, and they'll come into in parallel when you're trying to find the impedance across Vx. So do you remember what was the intrinsic resistance values for RD and RS? Yes?
RD is RDS,
RD is RDS, yes. Or which
RS,
is 1 by GDS.
yes.
Yes. And what about RS?
Approximately it will be 1 by GM.
Yes. And I mentioned it earlier as well. GDS is much less than GM, right? Which makes RD much greater than RS, right? Is this clear? This I'm talking about the values. GM is in few millisiemens, whereas GDS is in few microsiemens. So there is close to 1000, like order of 3 difference in GDS and GM. So that 1000 times of difference will come into picture for RD and RS also, right? So from there we'll get RD much greater than RS. But when you observe here, we have RD parallel to RS. So what will be its resultant value?
RS.
Yes. Here you'll see RS. Okay. Now let's look at this point. So at V out, you have drain of PMOS and drain of NMOS. So it will be like 1 by RDN parallel 1 by RDP. If let's say their GDNs are comparable, almost equal, so what we'll get? We'll get, oh sorry, it's resistance है तो directly it will be parallel. GD होने से 1 by होता है. So RDN parallel to RDP, and if let's say RDN is almost comparable to RDP, you'll get RD by 2, right? R parallel R will give R by 2, right? So now when you compare here, I told you RD and RS almost have a ratio of close to minimum 100 to 1000. So RD by 2 will always be greater than RS, right? This is clear, no? RD by 2 will always be greater than RS. Are you with me? Are you following?
Yes.
Okay. So when this is the condition, that means this node will have higher Z out. The Z out will be much higher. So what we need, R to be high and C also needs to be high. So we figured out where we'll get higher impedance. Now, like higher resistance. Now what about the capacitance? So is there a possibility that at this particular node we are getting higher R but lower C, and at this node we are getting lower R but maybe the C is much higher, so that this node becomes a dominant pole? Is there a possibility? That question comes to our mind, right? So for that we try to analyze what are the capacitances that come into picture and then see. So क्या हुआ? Yes. So now when this is the circuit, now let's see what are the capacitances that come into picture. Okay. So we know when there is a, let's say there is no body effect present. When I mean there is no body effect present, that means CSV is 0. Okay. So for now let's neglect that. That is CGS, CGD, CDE. Okay. So these three capacitances will majorly consider. Okay. So in this first one, you will see like 1, 2, 3. So this is CGS1. Here you will have CGD1 and CDB1, right? So since body and source are connected to ground, so I am directly connecting it to ground. Okay. So CDB1. right? Likewise, this transistor will have CGS1. Will this transistor will so does this transistor has CGS1? See, C is dq by dV. Okay, so will this transistor have CGS1 is the question. Will it have CGS1?
Its gate is grounded, AC grounded.
So there won't be any possibility of dV, right? So dV is basically equal to 0, right? Because it is a DC node, so there is no voltage fluctuation. And when there is no voltage fluctuation, there is no capacitance, no charge formation, right? No charge fluctuation. And when there is no charge fluctuation, there is no capacitance. So this CGS1 will not come into picture. Is this clear? Is this clear? Okay. I hope this is clear.
Yes, ma'am.
Yeah. So you will not see a CGS2. This was 2, no? So CGS2 into picture. What about CGS3? For this third transistor. What about CGS3?
0.
There also it will be 0. Acha. What about CGD2? Yes, CGD2. What about CGD2?
Yeah, it will be there.
It will be there, no?
Yeah.
Why? Because one node is AC node, other might be grounded. So it will come from a V out to ground. It will come like that. है ना?
Yes.
Now CDB का क्या scene है? So let's say we have shorted the body. Okay. Now here the quest is, if C is B, like V is equal to VB, then CSB will be 0, right? But what about for transistor 2? The moment you short your source and body, what will happen? This node is not grounded, right? So when we write CDB, at that point it will appear somewhat like this. It will be across your drain to this source, right? So this is how your CDB will appear. Is this clear? Why I am writing it like this, is this clear?
Yes.
This is the condition when your source and body are shorted. Okay, there might be another condition where what happens, ideally when you are designing your circuit and basically laying out your circuit, you only have one body terminal for all the NMOSes that you have and one body terminal for PMOSes you have. Generally that is the idea. So what we do, we connect body of NMOSes to ground and PMOSes to VDD, right? So if that is the case, then what will happen? Your CDB, that is your drain to body capacitance, will actually come between your output node and ground. Is this clear? Is this clear?
Yes.
This is the condition when your body terminal is grounded. But if this is the case, then your CSB will never be 0. Why? Because your CS, your source potential, is never at 0. Is this clear? Are you following? So there are two types of conditions. One, when your source and body is shorted, then things will be a bit different. When, let's say, your source remains there and your body is grounded. Now when you look at it carefully, so for first transistor there is no issue. Whether your body and source are shorted or body and source are grounded, it doesn't make a difference for your first transistor. Similarly, for your topmost PMOS, it will make no difference whether it is source body shorted or source and body both are connected to VDD. It will not make a difference. But where does that difference comes into picture? In these intermediate transistors. Because there the source node will have different potential. Rather than VDD and ground, it will be a floating node and it will have a potential in between VDD and ground. It is never fully VDD, never fully ground. There is a possibility, that might be possible, that your transistor is in cutoff and you will get that point to be, let's say VDD or let's say ground. There is a possibility, there is a chance. But you cannot say, you can never say. These nodes become floating. So when that is the case, at that point, these type of issues comes into picture. That is what I wanted to mention. Okay, so let's consider this body shorted, body grounded one, and for PMOSes, it is connected to VDD because it is a more realistic picture when we go for IC designing and works like that. So in that case, you'll also see a source body capacitor for transistor 2, right? So we'll get another another capacitance will be CSB2. Clear? Is this clear? Now similarly, okay, for this PMOS, we'll again have CGD3. CGD3. What about CGS? For transistor 3, what about the CGS3? Will we have a CGS3 there? For transistor 3, which is a PMOS, will we have a CGS3 there?
No.
No, because both are DC nodes, right? We'll again see a CDB because this will be AC grounded. So this CDB3 will come into parallel, right? And will there be a CSB here for transistor 3?
No.
No, there won't be any CSB. So if you carefully look into them, so these two nodes which we were talking about, so they have CDB parallel CDB, CDB2 parallel CDB3 and CDB1 parallel CSB. So considering these capacitances are almost comparable, so we can see two capacitances coming into picture for this particular node as well as two capacitances coming into this particular node, right? And if these capacitances are almost equivalent, then that makes their C almost equal, like C for first AC node and C for second AC node are almost equal. So what is the major thing that is playing role is the resistances, right? And these resistances had somewhat quite a large difference. At this node we were getting RD by 2, whereas at this node we are getting RS. So this RD by 2 is much higher compared to RS. So this V out node is your dominant node, or it will give your dominant pole. Is this clear how we found out the dominant pole? See, this analysis is very important. That's why I'm taking this much time in explaining, because this is one of the uh, most crucial analysis that we require, because always you need to find out what is your dominant pole. It is one of the major and most critical information that is required for your circuit. Even to analyze its stability, its bandwidth, for these type of analysis, you'll require this dominant pole. That's why it is very important to understand the concept of dominant pole. So did you get how we are calculating dominant pole? How we analyze dominant poles? Is this clear to everyone?
Yes, ma'am.
This is clear, no? So firstly, what you'll do, first of all, find out number of AC nodes. Clear? Then you find out the impedances or resistances to that particular node and capacitances across that particular node. Then figure out for which node you are getting higher RC value. So the higher the RC value, 1 by RC will be lower, and 1 by RC is basically your pole. So that's how you will get your dominant pole. Is this clear? So this is one of the major analysis that is required. Okay. Now talking about, we got the poles and how to calculate the poles. Now next question is how to calculate zeros. So for zeros, the idea is how many capacitances are connected. Yeah, this was for poles. For zeros, the idea is number of zeros is number of capacitances connected between input and output. So it is the number of capacitances connected between input and output. That's how we find out the number of zeros. Okay. So let's say, going back to the initial, this was the initial circuit, right? So here, what are the capacitances that we'll see? It is CGS 1, let's say 1, 2, CGS 1, CGD 1, CGD 2, CDB 1 and 2. So how many poles do we, how many zeros do we have in this particular circuit? It is the number of capacitors connecting your input and output node. How many capacitors are there which are in between your input and output nodes? That will give you the number of zeros. So how many zeros do we have?
1.
1. Because this is the only capacitor that is connecting our input and output, right? So we'll have a single zero. And what is the value of that zero? Yes, what will be the value of that zero? It is again 1 by RC only. See, rather it be a pole or it be a zero, it will always be 1 by R. Zero will also, you will calculate zero from 1 by R only. But now, which R that we will consider? That is the question.
Where the capacitance is present in that node, we need to we need to consider the resistance one.
So here This is the only capacitance that is connecting, right?
Yes, ma'am.
CGS1, CGD1, sorry. So this capacitor will come into picture. Along with this, you'll need the value of resistance also, R.
That resistance only will consider, ma'am.
So what is that resistance that you will consider? So see, it is connected between input and output, right?
Yes, ma'am.
It is connected between input and output. So you will see transconductance. So resistance, you'll write it as 1 by Gm. So the value of 0 will actually be 1 by Gm CGS. That is Gm by CGS. So this is the value of 0 that you will get. Is this clear?
Yes, ma'am.
Is this clear?
Yes, ma'am.
So here for
So, how this resistance 1 by GM came?
this, see, when we were talking about this particular nodes, AC nodes, we said across that node, what is the resistance and what is the capacitance that we are seeing. We'll simply multiply them and we'll say 1 by RC as our pole. Clear? But what about when we have a 0? Here what is happening is the 0 is connected between your input and output node. So there are two nodes which are coming into picture. So when there is input and output, so what is the relation that connects these two, input and output? It is the transconductance that connects, right? And talking
Yes.
about a MOSFET, the relation between input and output, we relate it through transconductance. So that's why I'm saying the resistance, I can simply write it as 1 by Gm, and the capacitor that is connecting these two nodes is known to us. So we'll simply use 1 by Gm as our R and the capacitance CGD as the capacitance. So 0 will be Gm by CGD. Is this analysis clear?
Yes.
Okay. So now we have analyzed how to find the values for poles and zeros in a given circuit. Now let's move on and solve the first question. And you'll understand why I stressed this point so much, because now we'll be going and analyzing all our circuits mostly through this method only, because it reduces your time as well as complexity of the circuit. Okay. So in this first question, what is asked is the value of pole at the out. What is the pole due to output impedance? That means at this particular point you have to find the pole. So what you will do? At this point you have to find the value of pole. So what will you do?
1 by RS is
Yes. So you'll find R out and you'll find C out. And for pole, what you'll do? You'll simply do 1 by R out, C out. So can you, by looking at this particular circuit, can you quickly let me know what is the R out that you will get? See, this is drain, this is source, this is gate. So first of all, tell me what is the R out that you will get? What all resistances will come into picture and how they'll relate, whether they'll be series, parallel, or some complex connection. What comes to your mind? First, let's discuss the R out. What will be the R out that you'll be getting?
1 by GM parallel RS.
Yes, 1 by Gm you will get, parallel RS you will get. Anything else that will come into picture? Look at the givens that you have. You have RS given, RD is given. Any other resistor term? No. So can you use something else? Acha, okay. 1 by GM, 1 by RS. This is fine, right? This you people understand how you are getting. But when I say you'll also get parallel RDS, can you understand this? If I say you'll get parallel RDS too, are you with me? What do you think? Is this correct or incorrect? Yes? What do you think? RDS should be there or not? What do you think? Okay. Why is it written as RDS rather than RD? What is the importance of writing RD and RDS? What is the difference that comes into picture when you write simply RD and RDS? Yes? Okay. So when you write RD, that means it is a resistance from drain to ground. What is the reference here? There is no reference, so the reference is ground, right? But when you write RDS, then it becomes drain to source resistance. So here the reference becomes source, right? So if the source is connected to ground, then you'll see this resistance from drain to ground. Now, in our case, what is happening is that the source is not grounded, but actually this drain node is AC grounded and the source is floating node. So this RDS will come like, so earlier it was connected. So let me show you. So this is drain, okay, and this is source. RDS means basically it is somewhat like this. This is your RDS resistor, okay. Is this clear? Now let's say if your source is grounded, that means your RDS will convert as RD. So it is from drain to ground. But somehow, as in our case, your source is a floating node and somehow your drain becomes AC ground, as in this particular case. What will happen is your RDS will actually become RS. So that is comes between source and ground. Is this clear? Did you understand what we are discussing right now? Are you there with me?
Yes, ma'am. Yes, ma'am.
So did you understand how this RS is basically becoming RD and RS depending on different conditions that we have? So it depends on. So it becomes RD when RS is ground, and it becomes RS, that is, it comes
When RD is
across
ground.
resistance when RD is ground. So in our case, what is happening? This is the condition that we are seeing in this particular circuit, right?
Here RD is ground, right?
Here so here your drain is grounded. So here ground is source, here ground is drain. Oh, sorry. RD होगा जब source is grounded and ये होगा जब drain is grounded. So in our case we have drain which is becoming AC ground. So we'll see this condition coming into picture. So that's why when we say R out, so we'll get 1 by Gm parallel to Rs parallel to Rds also, because this Rds will come like यहाँ पे आ जाएगा ये.
Output voltage.
Got it? Is this clear?
Yes, ma'am.
This is clear, no?
Next.
Right. Next thing. Now there is another thing that is this type of capacitance you see, when you see these type of capacitance between two AC nodes, so what happens is this capacitance gets shared between both the nodes, and this is known as Miller capacitance. Have you heard of this term, Miller capacitance?
Yes, ma'am. Miller's theorem.
Yeah,
Yeah.
Miller's
Yeah.
theorem. So what happens is whatever impedance you have over here in between, its certain part you'll see in this input node, and certain part of it you'll see in the output node. And generally what happens, so basically what happens is in the input side you'll see gain times your capacitance or impedance, and in output side you'll only see that particular capacitance 1 into capacitance, and in input side you'll see gain times of that capacitance. Okay, so this is the Miller theorem. Clear? This is also something that you can keep in mind. So because of this Miller theorem, what
1 minus
happens
AV,
is,
no, ma'am. Output voltage.
sorry,
1 minus AV into capacitance, right?
1 minus AV into capacitance, you are saying, okay, so what I am saying is the resultant capacitance that you will see. So 1 minus AV hone se bhi, it's like AV is much higher than 1, no? So 1 minus AV ko you can simply write minus AV. And since this is CD configuration, तो यहाँ पे तो minus AV आ जाएगा. If it would have been CS configuration, तो यहाँ पे negative capacitance होता. यहाँ पे negative gain होता for CS configuration, so it would have been plus AV. But I'm talking about this factor, that is, it becomes gain times of that.
Output voltage by input
Yes,
voltage.
yes. So it becomes gain times. So that is what another thing that I would like to highlight. So yeah, we found out R out. Now next thing that we are left with is to find out C out. So what will be the value of C out? Yes, what will be the value of C out?
CGS
Mm-hmm.
and one capacitance in between the one capacitance.
What one capacitance?
One zero. We found out one capacitance.
Ah. So I want the resultant capacitance between your at your output node. So I'm asking, what is that capacitance? What are the capacitances that you will see?
CGS
Mm-hmm.
and
The CS,
yes,
right?
yes,
And
ma'am.
how they will come into picture? So they will be actually parallel to each other.
And in parallel it is added.
Yeah. So
Capacity
CGS
added.
भी कैसे आएगा? It will come from output to ground, and the CS is also from output to ground. So these two are parallel to.
10.5.
Sorry.
10.5 picofarad.
What is 10.5 picofarad? Oh, you are telling me the resultant answer.
Yes, ma'am. Yes, ma'am.
So
See, parallel,
since
ma'am.
these
Capacity
are
together.
parallel, so when capacitances are in parallel, the resultant is their sum, right?
Yes, ma'am.
So this is what you will get. Now you have got your R out, you have got your C out. Simply for pole, what you will do? Oh my god,
Multiplication
I
and
filled everything. Yeah, so pole will be 1 by R out into C out, right?
yes, ma'am.
So this is what you'll do. So you'll get the final answer. Is this clear?
Yes, ma'am.
Is this clear to everyone?
Yes.
So hope this is clear. So the answer that you will get is, you can try and solve it. The answer is minus 145.38. Okay. So simply substitute the values. GM is given, RD, RS, everything is given to you. Just substitute the values and solve. You'll get the answer. I'm moving on to the next question. Okay.
Ma'am, one more, ma'am.
Yes,
The same
yes.
question we can found it by using Laplace transform, ma'am.
Uh,
By
Laplace transform.
output voltage by, if you divide it, I get if you convert these CGS into Miller's theorem, no, ma'am, if you
Uh,
divide it, you will draw equivalent circuit. If you convert it into output voltage by input voltage, you will be the transfer function, right?
right.
Yeah, with this also we can convert, ma'am. Is there a way?
So basically, uh,
Elmore delay, ma'am. Elmore delay. Actually, I did a one course on similar to like this, ma'am. VLSI interconnects. There we will find out transfer function. With they, if like this situation happen, we will divide that CGS. Will Miller's theorem will draw equivalent circuit, and then we will find out the output voltage by input voltage, and we'll convert it to Laplace transform. And in Laplace transform, first order divided by that Taylor series will convert into Taylor series, and that first order divided by that constant S40 will be the Elmore delay. There. In this way, here also, if you convert into transfer function, the upper part will be the zero side, means output voltage will be the zero, input voltage will be the poles, right?
no, so that is what I was saying. So transfer function, you'll get numerators and denominators.
Yes.
And numerator consists of zeros, denominator consists of poles. So this method that I have told you, that is 1 by RC method. So this is an easy method. It gives you, so see, the idea is it will not give you exact transfer function, but it will give you a very approximate transfer function and very close to the exact one.
Yes, ma'am.
And
63%, ma'am.
yeah, and why we are doing this is because, so here you only see a single transistor. There is, you can easily solve its small signal model, and you can find V out by V in easily. But when we go for cascade circuits or big cascade circuits from 3 stage, 5 stage, and even cascade of 3 stage, 5 stage, at that time it is not advisable to solve transfer function like finding V out by V in through solving all the components through small signal analysis, and it will take a lot of time, and you'll make a tons of errors in between, because it will be so huge that you'll be unable to figure out what's going on and where it is going wrong. So people came up with this easy method where you can simply see, when you have a particular node, and we simplified every node's impedances also, right? Like if you are seeing from a drain, what will be the impedance? That is 1 by GDS. When you are seeing from a source, what is the impedance? So 1 by GM plus GD, or it is close to 1 by GM. And when it is a diode configuration, then what is the impedance that you see? It is 1 by GM plus GD. So we have already simplified those and we have analyzed those. So keeping those in mind and using our previous analysis, we are trying to simply find out the transfer function. And that is what we are doing here. So we simply find out that particular node's capacitance and resistance, and we'll simply multiply it, and we'll take the reciprocal of it. That will give you a pole. Likewise, we also found out how to find the zero. And when you put all the poles and zeros together, there is a high chance that you'll get a transfer function, right? Because the moment you get poles and zeros, you simply put zeros in the numerator and poles in the denominator, multiply all the poles together, multiply all the zeros together, and when you open it, so you'll get a transfer function. But it's like, so it will be very close view. And another thing is, when you see the values of poles and zeros, here we have not considered S, right? That is the Laplace, what should I say? We call it.
Yes, ma'am. We
Uh,
grounded it, no, ma'am.
no, that's not what I'm saying. So for capacitance, Xc is actually 1 by Cs, right?
Yes, ma'am.
Right? But when we are finding the values for pole and 0, we are finding the exact value. So pole is 1 by S plus P, right?
Yes,
So
ma'am.
1 by RC will actually give you this P. This P is 1 by RC.
Yes, ma'am. Yes, ma'am.
And this S, which was that Laplace constant, that is j omega, we have not used that one. So while forming the transfer function, you'll introduce this also. And when you incorporate all the poles and zeros that you have found out, you'll ultimately see that you'll get a transfer function which is very close to the actual one. Like not exactly same, but very close. Because even while you derive the transfer function, there are many assumptions that we take just to reduce our human efforts for calculation. Like if we have some constant, we neglect that constants, and if we have something like I said, 1 minus AV, when we see 1 minus AV, the next step is we'll simply make it minus AV, because who will take care of that one, and because of that one you'll get a lot more terms coming into picture. So to avoid that, we simply simplify it and say it's like minus AV, right? Even when we talk about impedances, like from source impedance point of view, we mostly say it is 1 by GM. Actually it is 1 by GM plus GDS, and even if you perfectly calculate, you'll get even few more terms. That is, there is a possibility, but we neglect all those terms and we'll focus on the major part that we have.
We
So
approximate them.
this will also give us that approximate transfer function that we have from this method also, and it is much easier. That's why we go for this method.
Yeah. Thank you, ma'am. Thank you.
Okay.
Good.
Yeah. So hope this analysis is clear. So the next question is, the previous question it was asked to calculate the pole. In this question you have to calculate the 0. Okay. So how will you calculate the 0? We have calculated it already, no? What was the value for the 0? It was GM by CGS, right?
Yes.
Yeah. So we'll simply substitute like GM by CDS in the CGD in this case, but our diagram is this one. For this, yeah, yes. For this diagram, our Miller capacitance is CGS. So that's why I'm saying it is GM by CGS is your 0. Is this clear? So you can simply substitute the value of GM, CGS, and these poles are, see, poles and zeros are negative because these are stable systems. So when you want a stable system, your poles should always be a 0, and your 0 being less than 0 or negative increases the stability of the system. So that's why they are all given in negatives. Is this clear? The value is 198.648. The moment you calculate, you'll get to know. Is this clear?
Yes, ma'am.
Okay. So it's already close to 4:30. Should we stop here? Actually, I had another type of question. It is a little different type of question. So here, see, when frequency comes into picture, that means C ko you should, Xc you should consider. That is 1 upon Sc. Because this is the point where you'll see your frequency coming into picture, right?
Yes, so 2 pi f.
Yes, J to pi f. So that's why whenever you need frequency, you have to have its Laplace transform. So you'll simply convert this to 1 by S CGS, and what you have to find is output impedance. So output impedance, how we find out? So let's say a current Ix from here, and a voltage Vx is being applied. So your Z out will actually be Vx by Ix, right? Is this clear?
Yes, ma'am.
So you're getting one current ID, and let's say another current is I1 over here. So if I want to write Ix, can I write Ix being I1 minus of ID? So that means Ix being distributed to minus of ID. ID ka direction is downward, so minus ID will be upward, right?
Yes, entering.
Enter, yeah. So exiting from this particular node. So, and this is I1. So simply we'll write the expression for ID, write the expression for I1, and we'll add it and we'll get Ix. And we have to find out Vx by Ix to get this Z out. Okay. So will you be able to solve this I1 and ID? So I'll give you the expression that you will get. It is 1 plus SCGS RS by GM plus SCGS. This is what you will get as your Z out. The moment you try and solve, so ID, how we write ID? Sorry, ID we write it as GM VGS plus GD VDS. So you try and solve this and convert it in terms of Vx, okay? And another one is I1. So I1, how you will write? It is Vx upon 1 by SCGS plus RS, right? This point say ground तक का voltage by resistance will give you current, है ना?
Yes,
So
ma'am.
from here we'll get ID, from here we'll get I1. Usko simply you have to write it like I1 minus ID, and the moment you solve it and try to convert ID in terms of Vx, because this Vx is the only input, and when we are analyzing, this Vin will be shorted. We know this, right? Because at a time only single source can be there. All other sources should be nullified. So voltage sources will be shorted and current sources will be open circuited, right? So that's how we'll analyze, and this is the final expression that we'll get. And if we talk about when we substitute the frequency, the given frequency, and J being 2 pi, frequency was given 3.2 gigahertz. The final answer that we get for Z out is actually 42.99. Okay. So this is the final answer that you will get the moment you substitute the resistances, capacitances, as well as the frequency. Is this clear? So following up the next question, this question was simply changing the frequency in the above question, and you have to see. Now another question was there, which was basically looking at the trend. You have to comment like what type of behavior that circuit is showing, that output impedance is showing. Is it resistive in nature, inductive in nature, or capacitive in nature, or is it very low all the time? Is it very low? So it turns out to be inductive in nature. Inductive in nature means that with increasing frequency, your Z is also increasing. This means inductive nature. If frequency is increasing, your Z is reducing, that means capacitive in nature. And if frequency is changing, increasing or reducing, but your Z remains constant, that means resistive in nature. Is this clear? Why I'm saying this is this clear? Because XL is omega L, XC is 1 by omega C, whereas R is not a function of omega at all. So that is the basic question which was asked. Is this clear?
Yes, ma'am. Yes, ma'am.
So these were the few set of questions that I wanted to discuss, but it's okay. We discussed the basics, and I hope that is clear, the discussion that we had today. And if you don't have any further doubts, maybe we can stop here. It's already 4:30 now, and we can meet next week.
Sanjay Singh.
Thank you.